IEEE Std 1100.2019 Clause 4.25.12 states that if the equipment grounding terminal bar of the substation control panel is directly connected to the station ground grid and the equipment grounding terminal bar of the utility transformer is also directly connected to the station ground grid, the service entrance ground rod may be omitted. This exception applies to cases where the grounded terminal, that is, the neutral, of the utility side is already grounded at the utility transformer. In such cases, it is not necessary to ground the grounded terminal again at the sub-control panel. The reason for this exception lies in the concept of creating a single-point ground reference, which minimizes circulating current and voltage differences that can arise from having multiple ground points. When both the substation control panel and the utility transformer are directly connected to a common, robust station ground grid, it establishes an equipotential plane. This means that the voltage potential across the entire ground grid is essentially the same. If a separate ground rod were to be installed at the sub-control panel, it could introduce a slight difference in potential compared to the station ground grid. This potential difference, however small, can drive circulating currents through the grounding system, leading to increased electromagnetic interference, or EMC, and potentially compromising the effectiveness of the grounding system. The station ground grid serves as a comprehensive grounding network that interconnects all electrical equipment and metallic structures within a substation or facility. It typically consists of a grid of buried conductors, often made of copper, that are interconnected and bonded to ground rods or other grounding electrodes. The purpose of the station ground grid is to provide a low impedance path for fault currents to return to the source, ensuring that protective devices such as circuit breakers operate quickly and safely to clear the fault. It also helps to minimize touch potential, which is the voltage difference between a person's hands and feet when standing on the ground near energized equipment. By connecting the equipment grounding terminal bars of both the substation control panel and the utility transformer directly to the station ground grid, a low impedance path is provided for fault currents to flow back to the source from either location. This ensures that fault currents are quickly and safely cleared, and it helps to minimize the risk of electrical shock. Omitting the service entrance ground rod in this scenario simplifies the grounding system and avoids the potential for circulating currents to be introduced. Firstly, to elaborate on the equipment grounding terminal bar, this is a dedicated point within the substation control panel and the utility transformer where all equipment grounding conductors are connected. Equipment grounding conductors are the wires that connect the non-current carrying metallic parts of electrical equipment, such as enclosures and frames, to the grounding system. These conductors provide a low impedance path for fault currents to flow back to the source in the event of a fault. By connecting all equipment grounding conductors to a common terminal bar, a single point of connection to the grounding system is established. This helps to minimize the impedance of the grounding path and ensures that fault currents are quickly and safely cleared. Secondly, the direct connection to the station ground grid is crucial for ensuring that the substation control panel and the utility transformer are effectively grounded. This connection should be made using a low impedance conductor, such as a copper cable or busbar, that is sized appropriately to carry the expected fault current. The connection should also be made in a way that minimizes the length of the grounding path, as impedance increases with length. Thirdly, the utility transformer is the transformer that steps down the voltage from the utility's transmission or distribution system to a low voltage that can be used by the facility. The utility transformer is typically located outside of the facility, near the point where the utility's power lines enter the property. The utility transformer is an essential part of the power distribution system, and it must be properly grounded to ensure the safety of personnel and equipment. The grounded terminal, that is, the neutral of the utility side of the transformer, is typically grounded at the transformer location. This grounding provides a reference point for the voltage on the secondary side of the transformer, and it helps to prevent the build-up of static electricity. Fourthly, the omission of the service entrance ground rod is only permitted if the other conditions outlined in the standard are met. Specifically, the equipment grounding terminal bars of both the substation control panel and the utility transformer must be directly connected to the station ground grid. If these conditions are not met, the service entrance ground rod must be installed to provide an adequate grounding path. Fifthly, it is important to note that the requirements for grounding electrical systems can vary depending on the specific application and the applicable codes and standards. The IEEE Std 1100.2019 is a widely recognized standard for grounding electrical systems, but it is important to consult with a qualified electrical engineer to ensure that the grounding system is designed and installed in accordance with all applicable requirements. Sixthly, the benefits of this grounding exception include a simplified grounding system. By omitting the service entrance ground rod, the grounding system is simplified, which can reduce the cost and complexity of installation. It also reduces the potential for circulating currents. By avoiding the installation of a separate ground rod at the sub-control panel, the potential for circulating currents to be introduced into the grounding system is reduced. Seventhly, the station ground grid should be designed and installed in accordance with industry best practices. This includes using appropriate materials and construction techniques to ensure that the grid is robust and reliable. It also includes performing regular inspections and maintenance to ensure that the grid is in good condition and that all connections are tight and corrosion-free. The grounding system should be designed to minimize the risk of electrical shock and to provide a low impedance path for fault currents to return to the source. This will ensure that protective devices operate quickly and safely to clear faults and that personnel are protected from electrical hazards. Eighthly, when evaluating the need for additional grounding, it is important to consider the overall electromagnetic environment. In some cases, the existing grounding system may be adequate to provide the necessary level of EMI protection. In other cases, additional grounding may be required to mitigate specific EMI problems. A qualified electrical engineer can perform an electromagnetic compatibility or EMC assessment to determine the appropriate level of grounding for a given application. Ninthly, proper bonding is also essential for minimizing EMI and ensuring the effectiveness of the grounding system. Bonding is the process of connecting metallic parts of electrical equipment together to create a continuous electrical path. This helps to minimize voltage differences between the metallic parts and reduces the potential for circulating currents to flow. All metallic parts of electrical equipment should be bonded together, including enclosures, frames, and conduit. Bonding should be performed using appropriate bonding jumpers or straps that are sized to carry the expected fault current. 10thly, the IEEE Std 1100.2019 provides detailed guidance on grounding and bonding electrical systems. This standard covers a wide range of topics, including grounding system design, grounding electrode selection, bonding techniques, and EMI mitigation. The IEEE Std 1100.2019 is a valuable resource for electrical engineers and technicians who are responsible for designing, installing, and maintaining electrical grounding systems. In summary, the exception outlined in IEEE Std 1100.2019 allows for the omission of the service entrance ground rod at the sub-control panel under specific conditions. This exception applies when the equipment grounding terminal bars of both the substation control panel and the utility transformer are directly connected to the station ground grid. By meeting these conditions, the grounding system can be simplified and the potential for circulating currents can be reduced, improving EMC. It is important to consult with a qualified electrical engineer to ensure that the grounding system is designed and installed in accordance with all applicable requirements. This ensures that the electrical system is safe and reliable. In essence, the standard recognizes that a robust, interconnected grounding grid can sometimes negate the necessity of individual grounding rods, promoting a more streamlined and effective grounding approach. Always prioritize safety and compliance with relevant codes and standards when dealing with electrical grounding.